Okay, so uh, the foundation of microwave engineering course is based on Maxwell equations. And Maxwell equations are basically four equations which relate the source and the corresponding fields. Okay, so there are two types of fields that you will encounter. That is electric field and magnetic field. Now, the source of electric field can be charge, or it can also be changing magnetic field. Okay, and the source of magnetic field can be current, as well as it can also be changing electric field. Okay, so it's very important that you can write down the Maxwell equations mathematically, and as well as you should be able to explain what is the meaning or statement of that equation. So Maxwell equations can be represented in two forms. One is known as point form, and second form is integral. Also, this point form is known as differential form. So the first equation is divergence of D is equal to charge density. So this notation is known as divergence. Second equation is divergence of magnetic flux density is always equal to 0. And these two equations are basically two laws. This first one is Gauss's law for electric field, and the second equation is Gauss's law for magnetic field. And the conceptual meaning is, the first equation is telling you that whenever there is a charge at any point, it will produce an electric field, and that electric field will be either going out of that charge, or it will be going towards the charge, depending upon whether it is a positive charge or whether it is a negative charge. So this divergence means that something is coming out or something is going towards some point. And what is at that point? There is a charge at that point. So whenever there is a charge, there will be either outward electric field or inward electric field. This is the meaning of the first equation. So this tells us that if there is no charge at a point, then it means there will be no electric field that is coming out or going towards that point. That is the meaning of the first equation. What is the meaning of second equation, which is telling us that divergence of magnetic flux density is 0? The reason is because we don't have isolated magnetic charges. So as a result, there will be no point from where magnetic flux will be coming out or magnetic flux will be going inside. So this second equation is basically the physical limitation. In nature, there is no isolated magnetic charge. So that is the reason that the divergence of magnetic flux density will always be equal to 0. Similarly, the other two equations, which are related to curl operation, and you people know curl is represented by this notation. So you can either take curl of E. And in second equation, we will take curl of magnetic field. According to this third equation, which is basically Faraday's law. According to Faraday's law, the curl of electric field will be either due to change in the magnetic flux density with time, or if there is a magnetic current density, which is represented by this symbol, it can produce curl. Okay. So now this operation, whenever you take this operation on any vector quantity, this is known as curl operation. And what is the meaning of curl? Curl means that the quantity, that is in this case, the quantity is electric field. So curl of electric field means that that the vector electric field is circulating. It has a behavior such that it is rotating. So what can produce a circulating electric field? It can be either due to change in the magnetic flux density. And this is basically Faraday's law, which you people have already an idea that whenever some changing flux, magnetic flux passes through a circuit, it will induce an EMF. Okay. Changing magnetic flux produces electric. Fourth one, which is curl of H, it is basically Ampere's law. So according to this, circulating magnetic field can be produced either by current density J, or it can be produced by changing electric flux density. So these are four important equations that are basically foundation of microwave engineering. Any equation that you will use in this course will be based on these four equations. Okay. So you must be able to mathematically write these equations, as well as you should be able to give the meaning of these equations. Now, the important point is this point. Why these are four laws? As I mentioned, the first one, this one, this is Gauss's law for electric field. This is Gauss's law for magnetic field. This is Faraday's law. This is Ampere's law. So why we are calling them Maxwell equation? The most important point is, what was the contribution of Maxwell? Maxwell introduced this term. And this term is known as displacement current. Before Maxwell, this term was not there. And the problem was, if we don't include this term, then according to these four equations, the source of magnetic field, what is the source of magnetic field? Source of magnetic field is current. This one. This is known as conduction current. The normal current that we people are used to, that is the motion of electrons. So before Maxwell, people were of the idea that magnetic field is produced only due to conduction current, which means there has to be charges. There has to be current, there has to be charges which should be in motion. So if there are no charges, there will be no current, and as a result, there will be no magnetic field. So there was difficulty in explaining that if there is no current, there should be no magnetic field. But there was a possibility that even if there is no current, there people were observing that there is a magnetic field. So people were not able to explain that if there is no current, then how come we have magnetic field? So in order to answer this question, Maxwell introduced this term that even, just 1 minute. Okay, so these are four equations in point form. Similarly, you can also represent these four equations in their integral form. So maybe you are not interested in finding the relationship between fields at a point. You may be interested that there is some region, let's say there is some region, some area, and within this area you are interested what is the relationship of these quantities. So in that case, you have to use integral form of Maxwell equations. So the first equation, that is the divergence of electric flux density, this equation becomes the closed surface integral of electric flux density is equal to the charge enclosed, and charge enclosed is represented by the volume integral of charge density. Similarly, the second equation becomes the closed surface integral of magnetic flux density is equal to 0. Now it's very important. Many students may have made this mistake, that this circle within the integral is very, very important. If you don't write this circle, it means you are totally changing the meaning of Maxwell equation, which means you are making a fundamental blunder. So in your opinion, whether you put this circle or not, it is just a minor mistake, but it is not a minor mistake, because this circle means that you are taking a closed surface integral. And if you don't put this circle, it means you are taking an open integral. So the meaning is totally changed. So in that case, you are totally changing the meaning of Maxwell equation, which means that you are making a fundamental mistake. So make sure that you don't make such mistakes in your exam. Similarly, the third equation, it becomes closed line integral of electric field equal to rate of change of magnetic flux passing through a surface minus magnetic current passing through that surface. And it's again very important to see that I'm not putting circle over here. So this is now an open integral. So if someone puts a circle over there, so again, he will be making a mistake. Okay. Similarly, the fourth Maxwell equation in integral form becomes the closed line integral of magnetic flux density, magnetic field, sorry, is equal to the changing electric flux passing through a surface plus current passing through that surface. So these are Maxwell equations in their point form and in their integral form. Now, another important point that is important is that these equations, if you look at these equations are, if I focus only on the third and fourth equations, the first two equations, you can see that there is no time dependency. These two equations doesn't involve any time dependency. But these two equations, they involve variation with time. You can clearly see derivative of B and then derivative of. So the two equations which depend on time. So these equations will be valid irrespective of how B is changing with time or how D is changing with time. It doesn't matter. So these two equations will be valid irrespective of how B is changing with time or how D is changing with time. But most of the time, we will be dealing with situation where these quantities will be changing sinusoidally with time. So rather than solving these equations for arbitrary time dependency, we will solve these equations assuming that the variation with respect to time is sinusoidal. So as a result, we can write down an alternate form of third and fourth equation when we assume that time change with respect to time is sinusoidal. So let's look at that. So I will say for sinusoidal time variation, which is also known as time harmonic variation. So mathematically, sinusoidal time variation is represented by this notation, e raised to power j. So in electrical engineering, if anything is changing sinusoidally with time, so we represent mathematically this variation by e raised to power j omega. So if you go back to this equation, if this quantity as well as any quantity, so now we will assume that all of these quantities, the electric field will be changing sinusoidally, this B will be changing sinusoidally, this M will be changing with sinusoidally. So all of these quantities, similarly in the fourth equation, H, J, and D, the vector quantities, all of them will be changing sinusoidally, okay? So let's look at this factor that when you take a derivative of quantity which is changing with time, so what will happen? So whenever you take a derivative of something which has this type of variation, so what you will get j omega e raised to power j omega. So wherever you have d by dt, you can replace that thing with j omega. So this is what we can do. So now if you look at the third equation, whenever you have sinusoidal variation, so I will say for equation 3 will become and equation 4 becomes curl of h is equal to j omega d plus. What I have done is I have changed this part and this part. So if Maxwell equations are written in such a way that you see this factor, that is j omega factor, this indirectly tells you that you are assuming that quantities are varying sinusoidally. Now, another important change that we can make is these quantities. So we have B and D. B is, what is B? B is electric flux density. B is magnetic flux density. And what is D? D is the symbol for electric flux density. Now, what is the relationship of B with H, and what is the relationship of D with E? So the fundamental relationship is that B, magnetic flux density, is related to electric field intensity by this representation. B is always equal to mu h. And electric flux density D is related to electric field intensity through this parameter, that is D is equal to epsilon times. Okay. Now this mu is the symbol for permeability of the medium, and this epsilon is the symbol for the permittivity of the medium. So in these equations, in place of B, you can write this equation in terms of H. So the right hand side will become minus j omega mu H minus M. And similarly, this fourth equation, right hand side will become j omega epsilon E plus. So B and D can be represented in terms of this with the help of these equations. And these equations are known as constitutive relations. Constitutive relations. Now it's also important that I have used the symbol mu and epsilon. These symbols are used for absolute permeability and absolute permittivity. Okay, but we usually uh, we usually represent these properties with respect to free space. Okay, so for free space we use mu naught and epsilon naught. So free space is kind of a ideal medium with respect to which we compare different mediums. So for free space medium, this is mu naught, which is 4 pi into 10 to the power minus 7 Henry per meter. And this is the permittivity of free space, and it is equal to 8.54 into 10 to the power minus 12 farad per meter. So these are some important constants which you must remember as a student of microwave engineering, or even as a student of electrical engineering. You should never forget these constant values, and you should not expect that you should be provided with the values of these constants. Okay, this should be in your mind. It should be on your fingertips. Okay, so as I mentioned that if you are dealing with some media, so its permeability will be not be mu naught, it will be mu. So how you will relate mu to mu naught? We relate it through what is known as relative permeability and relative permittivity, which are represented by this notation, mu with a subscript r and epsilon with a subscript r. So relative permeability means that what is the permeability of the medium that you are considering, and compare it with the permeability of free space. And similarly, what is the relative permittivity? Relative permittivity means permittivity of the given media, which is represented by epsilon, and then you compare it with free space. So whatever number you get from this, that will be known as relative permeability of the medium, and whatever value you get from this, that quantity will be known as the relative permittivity. So these are some important quantities that you should know as a student of microwave engineering. So when I was using mu and epsilon over here, so these are actually the absolute permittivity and permeability. Okay, so let me point out this is absolute. Similarly, this is also the absolute value. So based on this equation, the absolute permeability is basically permeability of free space multiplied with relative permittivity and epsilon relative absolute permittivity of the medium is basically equal to the permittivity of free space multiplied with the relative permittivity. And there is another important point that I want to make, and that is regarding losses. So in microwave engineering, we will talk about that whether medium is lossless or whether medium is lossy. So losses, how we will quantify, how we will model losses of the media. So there are two ways through which we can quantify the losses. One is we can assign conductivity to the medium. What is this symbol? This is sigma, and sigma is the symbol for conductivity. From field perspective, if there is a medium and if it is lossy, so it means it must have some conductivity. This is one way by which you can assign losses to any medium. So it means if medium is lossless, so we will say that its conductivity is 0. And if medium is lossy, it means its conductivity will not be 0. And the other possibility is we will assign losses through permittivity, and we will say whenever epsilon is complex, it means medium is lossy. And this is how we represent. Okay, this lecture will discontinue because we have a 40 minutes time limit. So I will again start the meeting. So please join this meeting again by clicking that link. Okay.